Alrighty, folks. Good afternoon. Sorry for the several minute delay. I'm about to share with you the link. I'm putting it in the chat to sign up for your space mission presentation time slots. The date I'm going to put on here. This is going to be for next Monday, 6/14. All right, so please go ahead and sign up for your time slot. Just be mindful here, okay? If there's a gap between you and the person before you, and for whatever reason, maybe there's a 20-minute gap, you're going to be expected to go not at the time that you signed up, but after the person who came before you. So you can try to sign up for the time that you want, but we're going to pretty much be back to back. All right, so I'm going to give you a moment.
Professor, I have a question.
Yeah.
Sorry for interrupting you. So are we not presenting today?
No.
So
No.
we're presenting on the 14th?
Correct. In lieu of a final, you're going to give presentations.
Is there any way that I can present earlier? Because I have a graduation that I need to attend on the 14th.
At what time?
I believe it's like in the afternoon, like 12 to like 4. I had to ask my mother. It's for my little brother's graduation.
All right. If that's the case, you can join the evening section and give your presentation at night.
Okay.
Okay. So let me, while you're all doing that, it's just taking me a minute to put all these times in. Hold on. Okay. All right. Looks like 3 people that are here with us right now still have not signed up. So just let me know if you need the link. I can always repost it. I will be posting this on Blackboard, but if you come to class, you get the priority of signing up for the time that you want. That's just the perks of being here. Okay. So Alex, I would suggest that you just go ahead and sign up for an evening section time. This way, yeah, exactly. Oh, you know what? Hold on. I gotta slide everything down there out. You know what? That's fine. You put your information there, and I'll just move it after. I have to move everything down. Yeah, that's fine. Okay. So let's get started. All right, here we are. Share my screen. Oh, I should probably open up let me full screen my presentation first. Okay. Okay, there we go. There it is. Share screen. Okay, great. So today we are starting lecture 11. This is our final lecture. Next week on Monday in the afternoon and evening sections, you will all be giving your presentations that you've been working on. To anybody that has submitted their drafts, I gave feedback on Blackboard over the weekend. So you should have access to that if you submitted a draft And then you can go ahead and revise that over the course of this week. All right, so that's going to be next week on Monday. This is again our final lecture. And we're going to be talking about black holes and the origins of the universe today. That is what we want to aim to cover by the end of the night. So we've talked about black holes quite a bit already. And I think it's time that we put a formal definition to what a black hole is. Right? It is essentially a location in three-dimensional space that has so much mass compacted into such a tiny region that the amount that the gravity and the gravitational field caused by that much mass is so overwhelming that it actually causes this extreme warping, right? Instead of having like imagine taking a sheet of fabric or like a trampoline and standing on it, right? Like you can imagine a person standing on a trampoline and maybe what that trampoline might look like from a profile view, right? From a side view. And it would look nothing like the warping that you're seeing on this slide. All right, so this is like extreme warping. And this is really what we expect to see around black holes. All right, now to make a black hole, you have to take a lot of mass and you have to crush it into a very, very tiny amount of space. And so exactly how tiny are we talking about? Well, there was a scientist whose last name was Schwarzschild, and essentially calculated what the radius of an object must be based on its mass, what the radius must be in order for it to become a black hole. Right? So anybody could become a black hole, right? If you take them and you shrink them into a small enough amount of space. Right? I could be a black hole, you could be a black hole. Right now, I'm going to pull up, I don't know if my slides caught off, but I'm going to pull up a video for us to watch of this extreme warping. Okay, I believe that this is the right video. Give it a second. Hold on.
Hi there, welcome to Forward. Come on in.
I'll share my screen in a moment. Hold on, let me just make sure that's the right one. Sometimes they change. Yes, okay, this is it. All right, here we go. New share. Here we go. All right, so I always like that video. I think it's kind of mind blowing how massive these black holes can be. Right. So, but I think what I really wanted to show you was that beginning part where it talked about taking our sun and crushing it to the size of a small town, or taking the Earth and crushing it to the size of a peanut. If you could imagine taking all of Earth and crushing that much mass into such a small size, that's how you could make a black hole. So you'd really have to crush something into a very small amount of space. And a black hole is basically like, if you think about a star, where stars undergo nuclear fusion in their cores in an effort to basically keep themselves from collapsing in on themselves, right? So when you talk about the life of a star, it's this constant back and battle between gravity and pressure, or the outward pressure from the radiation. But once a star reaches the end of its fuel line, which for most large stars, that is iron in the core, right? Stars do not fuse any elements that are heavier than iron. Once these very massive stars reach, the point where they have inert iron cores, they can no longer sustain themselves, and they can no longer, hold themselves up against their own gravity with this outward pressure. And so gravity wins. Now, when one of these supermassive stars, or when a massive star collapses, it can leave behind one of two things. One is a neutron star. All right, a neutron star is essentially this giant, basically floating sphere of neutrons. No protons, no electrons, just neutrons. And a neutron star can support itself under its own pressure, right? Because neutrons can only be squeezed into so much space before gravity can no longer shrink them down anymore. But if there is a gravitational, or rather a stellar core that collapses in on itself and is left with more than 3 solar masses, meaning it has more than 3 times the mass of our sun, it wouldn't be able to support itself under this sort of degeneracy, this neutron degeneracy pressure. And so gravity would win. And in that case, it would cause it to collapse into a black hole. So, black holes really only happen as a result of the supernova of very, very large, supermassive stars, right? We're talking like supergiants. When our star eventually dies, when our sun goes, it's not going to leave behind a black hole or a neutron star. It's just not heavy enough. Our sun will leave behind a white dwarf. Now, a lot of funny things happen around black holes. And one of those things is that time is experienced differently. That gravity somehow affects the passage of time. And based on this image, maybe you could figure it out that, the closer you are to a black hole, the slower time passes for you. So just out of curiosity, how many of you, and you could just put in the chat yes or no, how many of you have seen the movie Interstellar with, I think, was that Matthew McConaughey and, I can't remember who else. I think Matt Damon's in it. Somebody else. Okay. Well, I can't show it because then I can't really post our lecture to YouTube. But in the video, basically you have this sort of dystopian future, the world is basically ending. Earth is no longer able to really sustain life. And so you've got people from NASA working on getting us off the planet. And Matthew McConaughey and his team take a trip through this like wormhole, and they somehow end up in this other part of space where there are these planets that they're exploring for habitability. And they find that all of the planets are awash. None of them work, and they don't really have the fuel to get back to Earth. So they decide to do like a close flyby on this giant, supermassive black hole and use that energy to sort of slingshot themselves around so they can get back through the wormhole and return to Earth. And what ends up happening is when they take this sort of gravitational assist using the black hole, time passes more slowly for them. So when they actually make it back to, Earth, or not really Earth, but like, okay, well, I'm not going to give away the whole plot line if you haven't seen it, because it's a good movie and you should see it. But basically, everybody that they left behind when they left for this journey aged by like 90 years or so, 80 something years, for what them felt like 10 minutes, right? Like this one maneuver cost them 80 or something like that, like 80 years of life with everyone else, because people that are farther away from black holes experience time more quickly. So like, it's often, there's something often referred to as the twin paradox, right? You have, an identical twin, one stays on Earth, the other gets on a spaceship and travels, around a black hole or something like that. The one who traveled around the black hole will have aged less. And when they come back, their twin could be many, many years older than them. This is obviously not something that has ever happened, but this is more of a thought experiment. But in any case, gravity pulls on time, and it slows things down. And we need to account for that with a lot of things that we use in our day-to-day lives. So, for example, although the Earth is not as massive as a black hole, Earth has a gravitational field around itself. It's a pretty strong gravitational field. We are able to keep things in orbit. There's a moon that orbits our planet. And the further away you get from the Earth, the weaker that gravity gets. So time passes more quickly the farther you are from Earth's surface. And we use a lot of satellites. We have a lot of things that move through space and experience time differently than we do here on Earth. So like satellites, for example, have these clocks that basically monitor or are based on the motion of atoms, right? So they're very precise satellites. Einstein has two theories, right? One of them is special relativity, which essentially says that things that are moving faster experience time more slowly. And then he also has this other theory of general relativity, which has less to do with motion and more to do with gravity, that things further away from large sources of gravity actually experience time faster. So let's consider how both of these might affect a satellite. If you have a clock on a satellite, according to special relativity, the satellite clock is going to run more slowly than a clock on Earth, because the satellite's moving faster relative to us on Earth. Right? The satellite orbits the Earth every 96 minutes, I think, the International Space Station. And so experiences time much more slowly. But those satellites, let's just use the International Space Station as an example. is also further away. And that actually causes it, time to run a little bit faster. So these two effects of special relativity and general relativity almost negate each other. But when we look at the clocks that are in space, or the satellites that are in space, their clocks need to be adjusted by about, I think here I have 38 microseconds in order for, these clocks to stay synchronized with clocks on Earth. So this is something that people think about all the time when they're building satellites and technology that goes into space. Okay, so take a moment. We're gonna have everybody type their answer choice into the chat. We're not gonna penalize anybody for having the wrong answer. Just showing us where we're at. If you want, you can message privately directly to me. In fact, I'll make that the only option. Nobody will see your answer but me. Please go ahead, type into the chat, A, B, C, D, or E. Come on, folks. I'm waiting on all of you. I'll boot you from the meeting if you don't type an answer in. It just means that you're not there. No point in having us wait for you if you're not there. Questions at the top of the page. It's a finish the sentence question. Ten more seconds. Five, four, I'm gonna boot people. 3, 2, 1. All right, let's see who didn't answer. All right. Boom. Removed. Okay. Moving on. The answer is D. Right. So again, what we're saying is the presence of mass causes the warping of space-time. All right. Now, if there is a significantly larger amount of mass, right, and we're talking about like the remnant of a star, a large amount of mass squished into a small amount of space, that can create a black hole. All right. But just the presence of mass in general causes space-time to curve. Okay. According to Einstein's theory of general relativity, the stronger a star's gravity, blank. The stronger a star's gravity, the weaker its pull on another star will be, the slower time runs near it, the weaker the X-rays we see from it, the smaller the event horizon will be of the black hole that it makes, the less space-time around it will be distorted. All right, again, put your answer into the chat. Still waiting on everybody to put an answer in. 10 more seconds. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. The answer is B. All right, again, just going back to the slide from before. Gravity pulls on time and slows it down. Right, gravity pulls on time and slows it down. Now, one of the big questions that has, been really challenging until quite recently is proving the existence of a black hole. Because you can't see a black hole. Right? It doesn't emit light. Right? Black holes are essentially so massive that the curvature of space-time becomes so warped that once light falls into this well, and again, if you're thinking about the curvature of space-time, you could think of it like this, right? It's like a well that you fall into. The warping is so extreme that light can fall into this and not be able to get out, right? Like energy and mass and this and that are trapped in here. So there comes a point where light can't actually escape the black hole. That's how strong the gravity is. And that's why it appears totally black. So how do you find something that doesn't emit light? Well, there are a couple of things. Right, so for example, here's the center of a galactic group of stars, and let's see here. I will share my video. It's like 14 seconds. Give it a second. So, hold on. So Alex, to answer your question, black holes come from supernovas. So a supernova is the collapse and explosion of a supermassive star, and a black hole would be a remnant of that. A black hole is what's left behind. So what we're looking at here, and I'll play this a couple of times on repeat. Right, there's a black hole somewhere in the middle. Now we can't see it, but we can see the stars that orbit near the center of this galaxy, and these stars look like they're based on their paths. They're orbiting around something at the center there, and so that's some example for evidence. Alex, what do you mean by your question? And again, I'm the only one that can see your question right now. So if you can elaborate, if you could turn your mic on, that would be appreciated.
So, like, how the black holes usually consume everything in its path. So how come when the stars are orbiting around it, they're not getting sucked in and completely like evaporated from existence?
Okay, so that's a good question. Let's consider the Earth and the sun, okay? Let me stop that share, and I'm going to share a whiteboard screen instead that I can write on. Okay, so consider the Earth and the sun. All right, so there's the sun, and here's the Earth, and the Earth orbits around the sun. Right, so this is the Earth's path around the sun. Now, what if we took this sun? Oh, let me resume screen share. Can we see now? Or my, hold on. Can we see my screen share?
Yes.
Great. So what if the sun was just replaced with a black hole that has the same mass as the sun does? So imagine we took the sun, we squished it into a very tiny amount of space, right? Like that. What would the Earth do? Would the Earth get sucked in? Would it just keep on traveling around, business as usual? Now, a lot of people go ahead and think that because it's a black hole, the Earth's going to get sucked in, but that's not quite right. Right? So what's keeping the Earth in orbit is the curvature of space due to this mass. This is the same amount of mass as the sun, and so it's going to create the same amount of warping around it until you get very close. Right now, we're talking about something that we can't see, right? We can't see a gravitational field, but we can sort of visualize it like that picture on the title slide, where you could take like a two-dimensional sheet and basically, pinch it at the bottom and pull it down, and it warps the fabric of the sheet. Except we're doing that here with three-dimensional space, and I wouldn't even be able to tell you what that looks like, because that would mean you're taking something three-dimensional and you're making it four-dimensional, which we just can't really wrap our heads around. But like the curvature, if you're thinking about like the fabric of space-time, might look something like this, right? Where it only gets like really extreme around the black hole. Right, so the Earth would pretty much just travel around business as usual. Right, so just being a black hole doesn't mean that you automatically eat everything that orbits around you, right? But if something gets too close, and by that I mean like within the event horizon, then that would happen. Then it would eat it. Right? Anything that falls into the event horizon doesn't come back out. Okay. So let's continue on here. Right, so we have stellar black holes, intermediate black holes, and then supermassive black holes. And these three categories are essentially determined based on the size of the star in terms of its mass, right? How many solar masses does it have? And these are the different ranges. So again, just to quickly summarize, what is a black hole? It is an object whose mass is so high and it occupies such a small volume that light can't even escape it. And that's why it's a black hole. Because there's no light coming off of it. Now let's think about what it would be like to visit a black hole. As I just mentioned with the Earth and the sun, like you can orbit a black hole, right? You can orbit it and not get sucked not technically, I think, let me say this thought, and then maybe that'll change your perspective, Alex, being that you're the one that brought it up before. Technically, the Earth is falling into the sun. Right now, every year since the Earth has existed, it has just been constantly falling in towards the sun. And that's because the Earth is curving off of the path that it wants to travel, which is a straight path. Right? But we know that Earth travels around like an elliptical path, and that's because of the sun. So the sun is constantly causing the Earth to fall in, but because the sun doesn't have, like if we were to take the sun and increase its mass and not change anything about the Earth or the size of its orbit, the Earth would start to fall in, because then the gravity of the sun would be too large. But the Earth just continues to fall around the sun, and it'll never actually get much closer to it than it currently is. Right? So you could orbit around a black hole the same way. You can orbit around a black hole. Just the fact that you're orbiting around it, that is falling into it. But you're not getting sucked into the point that you disappear, unless you get too close. All right, there is a point where you get too close, and that is the event horizon. Now, what would it be like to actually fall into a black hole? This is an interesting thought experiment.
Professor.
Yes.
So is that why our Milky Way is like in a spiral, because there's a black hole in the middle of the Milky Way?
That's not quite why it's a spiral, because there are other galaxies that are not spiral galaxies that still have Milky Ways at their center. So,
Okay.
so that's not totally it. But that being said, most galaxies do have black holes at their centers, because black holes are able to hold a lot of mass together. Right.
So as you say that we're not able to see a black hole, but don't black holes shoot fire from its ends, like a string of light from its ends?
So it's not fire. It's something called Hawking radiation. And as time goes on, there are these small streams, but the point is that you can't capture them visually. Right? Like you couldn't see a black hole with your eyes because there's no light coming off of it. So, I mean, I could talk more about that later. But yeah, I mean, I'll put some articles up for you, linking to Hawking radiation. Not something I was planning on discussing, but I'm glad that you're interested in it. So if it's all right, Alex, I'm going to move on. Yeah, exactly. So Dina, I know nobody else can see what other people are writing in the chat. Let me change that so you can all. Respond to each other. So Dina just said, so it's just invisible to the eye. Yes, it's invisible to the eye, and most light gets sucked into it. Right? If light falls into the event horizon, it doesn't matter what kind of light we're talking about. Gamma radiation, X-rays, ultraviolet, visible light, infrared, microwaves, radio waves. All of them can fall into a black hole and not come out. But then black holes eject radiation from their polar regions, like these jet streams. And again, I will post some articles about that on Blackboard for you to read. But I want to talk about what it would be like to actually fall into a black hole, because this is something that interests a lot of people. So let's say that you're falling into a black hole. You're falling in feet first. Okay, so it's like imagine just flying over the earth, like skydiving out of a plane, and then just falling towards the ground feet first. So that's how we're dropping into this black hole. Eventually, you're going to get so close, you're going to fall in and get so close to the center of this black hole that the force of gravity on your feet is actually going to be orders of magnitude greater than the force of gravity on your head. Right? Now, what is that going to do to you? Well, that's going to cause you to essentially rip apart from yourself. And it won't be pretty. It'll be like atom by atom, you get ripped apart. I feel like that's something that you'd probably see in, like, I don't know, an anime or something. But what would that be like to experience? Well, your time is also distorted as you fall into a black hole. The further in you fall, the slower time, the slower you experience time. So if your head is the last thing to fall in, right, then time is moving faster for your head than it is for the rest of your body. You're basically watching your limbs atomize and shred off your body, which would just be horrible. I feel falling into a black hole has to be top 10, one of the worst ways to die. And I don't think anybody has ever experienced that. So it would be pretty crazy. It's actually, there's a word for it. It's called spaghettification. You literally get turned into a stream of particles, like a spaghetti stream of particles. Really, really crazy stuff. Okay, so this is actually where we're gonna stop for this afternoon section. And then in the evening section, I'm going to just talk a little bit about the origins of the universe. And that is going to be it for our semester in terms of lecture. So again, just make sure that all of your assignments are up to date, and make sure that you have participated in the discussion questions that you were supposed to participate in. And with that, I'm going to stop my sharing, and I'll stick around a little bit for anybody with questions. And everybody else, you can head out and enjoy the rest of your week. And make sure that if you have not signed up for a time slot, make sure that you sign up. Next week, it is incredibly important that you are all here for the entirety of the class time, right? If you're all putting in a lot of effort, I hope, to make your presentations enjoyable and strong presentations, and you want to make sure that you give your classmates the courtesy of sitting through their presentations, just as you would want people to sit through yours and look at your work. And so with that, have a great week, everyone. I will see you all next week. All right. So just make sure that your slides are ready, and I will see you then. Okay. Alex, you have a question?
So for the afternoon class, like, how do I get in? Do I just use the same link to pop up?
You mean the evening class?
Sorry, you cut out.
You mean the evening class?
Yes.
Same link.
Okay. So I just pop up at 8 o'clock for it, correct?
Yeah, that class begins at 8:15.
Copy that.
All right, great. All right, everyone. See you next week. You're very welcome. Take care.